Hi everyone, here is Sébastien Sans. I'm FPGA application specialist in eFPGASIM team. I want to thank the marketing team to invite me today to represent our product and my team to this event. It's always a great pleasure to come here to represent our company. Today I'm going to make a live demo about an hybrid car motor drive, and I'm going to talk about especially fault insertion at the model level, and I'm going to show you the accuracy of that model. So to start, so here is the setup we're going to use today. So that's OP4510 coupled with OP8665, which is a controller, a TI controller that we've built a platform to host that controller that is compatible with our our simulator. So I'm going to show you that on my webcam. So now you should see it. So at the top here, you have the DSP here. So this is the OP8665 that hosts that DSP. The pin out, the pin at the back here are compatible with our simulator OP4510. So I hope you can see it. Oh, I moved the webcam a little bit. Here we go. And basically, I made a control for my hybrid car application, and the controls here have a couple of buttons, to all that stuff. So I'm going to show you how the interface looks like first. Sorry, here we go. So what we're going to simulate today is boost followed by a DC-AC three-phase inverter followed by a motor. So all the power conversion part is done in EHS. So François just told us about EHS, so I'm going to demonstrate that to you, how it's managed inside the Simulink model. And so everything is in HIL mode, so we have the real controller in the loop. By the way, you can easily see I'm going to share the scope sometime if you want to see what happened on the scope. So I'm going to share it sometime when it's important. So everything is recording on the scope. At the same time, it's simulated, and I can monitor it in this interface. So so first, I want to show you the model that is used to make that simulation working. So as you might know, if you work with a OPAL-RT product before, the simulation is hosted in the simulator, which is a CPU-based simulator. But in our case, the CPU simulator is just here for the monitoring and to control the FPGA. So inside the master subsystem here, which is the one that runs in real time, in contrary to the console subsystem here, which is the one that runs on my host PC for monitoring purposes, I will have inside the master subsystem a EHS block. So inside here I have the model part. I have one EHS block here, and I have one PMSM block. So for EHS block, this block take a simple system model as a reference for what we're going to simulate in the FPGA. And what it does basically, it takes that model, it extracts the netlist, the information, calculate the equation, and push that to the FPGA. So the great advantage of that solution regarding coding directly inside the FPGA is that recalculating the equation takes only a couple of seconds. It's not very long, and you don't have to recompile the FPGA every time you make a modification to your netlist. So I'm going to make a quick example of what you could do. So for example, I'm going to go inside MATLAB and open my circuit diagram I want to run inside the FPGA. So this is a DC AC PMSM drive example. I have my boost here, and here I have my inverter with the interface that's gonna interface with the machine. And if I want to change a parameter, so let's say I want to change the DC capacitor value, I could go here and select a new value for my capacitor. So it was 4.5. I'm going to select 5, let's say. I'm going to apply my modification, save, and then I only have to update the CPU model to be able to apply my change to the initialization file of EHS. Then I'm going to restart my simulation. So I'm going to reset. And I'm going to restart the simulation to have the new value applied. So that whole process takes only a couple of minutes to do. It's not a very long process to do. If I would have to do it, you know, with I mean, if I would have to recode the FPGA, it would take like 4 hours. But with our EHS solution, modifying parameters, modifying the net list is very easy. So I'm going to connect to the model. So you'll see. It'll take a second. So right now, if I share my webcam, there is nothing on the scope. And then everything will come back up, and you'll see that the controller will take the hand again on the model and control the simulation. Okay, so you see on this on the scope there is some waveform appearing. Okay, if I come back here, you'll see that everything is running now, and my interface is loading and running as well. So, so this is one feature I wanted to show you. What is the workflow with DHS? How I change the circuit very easily. So now I change the capacitor value, but I want to make change on the fly because sometimes you want to insert a fault, and basically inserting a fault is like inserting a resistor that's going to pass from a value of 1 megaohm to 1 milliohm instantaneously. So we made another feature which is called a scenario feature that allows you to actually insert parameter variation on the fly during the simulation. So how it works, it's pretty easy as well. I'm going to shut down the webcam for a bit. Okay, so it's very easy. You have an Excel sheet that contains all the system parameter. So I create already the Excel sheet. So I'm going to show you that Excel sheet. Try to zoom in for those that doesn't have a very good resolution on the screen. I hope it's going to be okay. Okay, here we go. So and now you see this is all my default value for all my elements in the circuit. And then if I want to make a modification of my parameter, I have a list of scenarios available here. So for this circuit, I can make up to 112 scenarios, different scenarios. So what I've done to my circuit to make fault is I inserted some resistors here that are not real resistor, but the default value of these resistors are very high if I want to make a short fault. So the base resistor is very, very high, and when I'm going to apply a fault, I'm going to put a very small resistor. So you're going to connect the two net together. So here it's for the A bus fault. So this is the A net, and I place a resistor of 1 megaohm here. And when I'm going to apply the fault, so A bus fault is here, I'm going to put the resistor value to a very small value, so 1 milliohm. So this way, it's very easy to apply any fault you want because you can place any resistor you want everywhere in the circuit. So this is one feature, very interesting if you want to do fault insertion at the model level. The other thing is if you want to change, for example, the impedance of, I don't know, the boost capacitance on the fly, or make a very big boost inductance variation, this is something that's possible, and this is something I'm going to demonstrate as well. So if I come back to the model here, so I linked my scenario to that button here. And in the CPU model, I have an input here, and basically I'm going to control that constant here, which is a scenario ID, on the fly from the panel, from the test drive panel, and I'm going to apply a fault. So first fault I'm going to implement is a phase-to-phase fault. So I'm going to connect the A phase and the B phase together. So here you see I've applied the fault, and I have VA and VB that always match together. And you see my current went dramatic here. It's a very bad current, which is normal. My controller is a very basic one, so he won't stop when he sees a fault. It's going to keep on running anyway. So this way I could do my demo. I'm going to put it back to normal. So you'll see, my controller doesn't like when a fault happens. It becomes a bit unstable. So I have to reset it like you would do on a real controller. Okay, so I reset the controller. I can show you, I have a couple of buttons of the controller that helps me to reset it. So, okay, I can reset. And then it's back on. Here we go. I have two control of my controller. That's a very basic controller. I have one control for the voltage of the VA. So the blue waveform is VA. It's the voltage. So I can control the boost voltage. So I can control the DC linker voltage. So it's a very interactive demo. And I can control the torque in my machine. So I can control the current. So current control and boost control demo. So now back to the faults. So yeah, the first fault I've made was a face-to-face fault. So I think it's one of the most basic faults people would do. The second most basic fault is a face-to-ground fault. It can happen pretty easily. So I'm going to demonstrate this one as well. So you see the A current stays always to 0. And as before, the current went a bit crazy. And I'm going to come back to normal. Okay, my controller is now a bit under shock, so I'm going to reset it again. Here we go. Back to normal. There is two more faults I want to show you that are very easy to see. So the first one is phase open. So when I open a phase, there is no more current on the phase. So that's easy to see that the fault has been applied. And now the last fault I want to do is the boost inductor failure. So let's say I have, when I have a failure on my boost inductor, what's going to happen is the inductor value will go down. So I change the inductor value to a very small one, and you see that the current here is crazy. It's oscillating like between minus 200 and 600 amps. So it's a lot of current. Obviously, it's not the only feature we have with DHS. We have plenty of other ones. So for example, it comes with a tool that helps you to map all your analog output to your interface. You can apply mean, max value, saturation value. If your controller doesn't support 16 volts, you can put it to 5 volts. It comes with gain, offset, all the settings you need. We have a pretty good resolver encoder tool that you can actually modify the gain of resolver sine, cosine, and you can also apply fault to these. So it's a very good tool for testing. After that, we have a good view of VD, VQ applied. So now my boost inductor was in failure mode, so this is why my VD, VQ wasn't very stable. We have a lot of different features here. That's very interesting. We have a VDQ moving average function as well. So if I come back here, you see VDVQ will be very steady. Okay. So, oh, yeah, it's like a bit oscillating. Okay, reset the controller. Here we go. So now, next thing I want to show you is that everything is hosted in the CPU model. So that means if you want to implement your own model with eMegaSIM inside the CPU model using a simple system, RTMS or SSN, you can couple EHS, so you can couple the FPGA-based simulation into a bigger ecosystem. So this is one thing you could do. If you want to use FEA for your application, so because you want a very good model, we have this model that has 4 times more table size than before. So we made a pretty big table for this model, and it's compatible with GMAC, RT, NCS, Inpolitica, a lot of FEA providers. As you can see, today I'm using a FEA model, so we have those little harmonics on the torque and on the current that you wouldn't see on other simplified model. It's something that some controller needs to run properly, and you have some functional controllers, for example, the cogging torque compensation that exists that could be tested with this kind of tool. So I'm going to conclude a little bit about this this demo. So I think that a HIL is really it's a tool to increase the test coverage. And what we show here today is that with the fault capability, I haven't showed the scripting capability, but here you can put a Python script as well that control anything in this model. So we have the scripting compatibility, we have a model that is accurate, we have a model that can be scaled to a bigger ecosystem, so it can be integrated with a bigger system to test the validity of your component inside a bigger system. So all of this thing plus the compatibility with driver, I mean, I have so many things. It's a very complete solution. All of those things allows you to increase your test coverage a lot. I mean, compared to a dyno bench, that would be more restricted because you need to respect safety, you need to respect schedules of other team using the dyno bench. HIL-based simulation is a lot more flexible and allows you to perform tests a lot more tests that you would do with the dyno bench.